lectures. But here you go, another one remembered. Okay, we got some interesting stuff today. Well, of course, at least I think it's interesting. Going to remind ourselves about the big three types of equations for scalar quantities with second order partial derivatives in two variables. We got elliptic, hyperbolic, and parabolic. So we've got the Laplace equation, Laplace or Poisson. We've got what did I say, hyperbolic next, that's the wave equation, and parabolic is the heat equation. And what I'll show you is that there's a reason why we studied these, because they are generically appearing in any PDE if you look at them locally under changes of variables. So with that in mind, oh, and let me say what else have we got, and then we're going to start talking about transform techniques. I'll remind you about the Fourier Transform, or tell you about the Fourier Transform if you've never seen it before, if it's not your friend yet. And we'll use it to answer a few questions in semi-infinite domains, which will give us a real tool to look at a PDE and understand how it's going to behave. Okay, so let me share. And let me reduce the window on this screen. Okay, well, oh, here we go. So that I can see the Slack channel. Okay, so we're going to have a general constant coefficient PDE in two space variables. And of course, for some of the types of equations, one of the variables that I'm going to pick will really have a time-like character. So I'll have the vector x with two components. And if I'm going to talk about the general constant coefficient PDE, I should say second order. By second order, I mean it can have up to two partial derivatives. I've got the A second derivative with respect to the first variable. I've got the C second derivative with respect to the second variable. Now, I'm going to have a coefficient in front of the mixed partial derivative. And just to make some of the algebra a little bit cleaner later on, I'm going to call it 2 times B times the mixed partial derivative. And then I'll have lower order terms. I'll have a d du dx1 plus e du dx2. And if it's still linear, I would put an f times u, but I want to save f for the right-hand side. Okay, so we're going to drop the lower derivative terms when the higher order derivative terms, the second order derivative terms, tell us something. I played with this off and on, trying to figure out the best way to do this. There's some linear algebra that gets mixed in with chain rule. If you've done this before, this is one of these great things, you know, about some textbooks. Professors say, oh, that's a great book. And yes, it's a great book if you know the material already, which means it's not necessarily a good book for students. So there is a good way to do this with Einstein summation notation, which is excellent when you've already seen it and you know how it should go. It's the cleanest way to do it. So I'm going to do a little bit more work than that. Hopefully it will be useful for people who haven't seen this before. Okay, so I'm going to make a matrix to describe these terms. I'm going to have a matrix A, which will be 2 by 2, right? And my matrix is going to be the matrix with entries A and what have I got? C and B and B. This is where the two B's are going to come from. Okay, so it's notice it's symmetric. And so, well, it's going to have real eigenvalues with orthonormal eigenvectors. Oh, that's going to come up in what follows. In the notes, which are from the last time I taught, oh, this is from Math 401. Apparently, when I taught Math 401, the one time I did it, the students who had had a Math 400 the previous term had not seen this. This is a classic topic in Math 400, so I was surprised. So I wrote up some notes for them. Anyway, in those notes, it says, assume that this matrix is not invertible. I have no idea why that sentence is there. All we need is that this matrix not be completely trivial. It has to have at least rank 1, okay? So it's non-zero, we could say, is interesting. Invertible is fine. In fact, for most of the cases below, we'll have it as an invertible matrix. I'm also going to have a vector L, which will have the components D and E in it. Right? Okay, so now I can write the PDE. And if you've seen Einstein summation notation, now you can see why it's something that's good. Okay, and I'm going to even write it out as a double sum. I've got the Aij, and then I've got the D2U dxi dxj. And I'm going to have the sum of I equals 1 to 2 Li du dxi. And this is all equal to f of x. So you can think about that for a minute. If you've seen this game before, then you go, oh, that's, of course, right? And if you haven't, then maybe you have to do a little bit of thinking, right? To see that those two forms are equivalent. And at least you can look at the I equals 1, j equals 1 term. You get A11, which is A. And then you get the second derivative with respect to x1 and x1 again, right? It's 1 to 2. 1 to 2, 1 to 2. Right? Yeah, it's just a, well, okay, right? It's a tensor product if you want to look at it that way. And if you've seen Einstein notation, then this would be, you would write this without the sums. I'll say Einstein summation. You would probably write this shorthand like Ui, Uj. Oh, sorry, Uij, where the I and the J subscripts are meant to be the derivatives shorthanded. And you don't write the sums in Einstein summation notation. Every time there's a repeated index, then you know you're supposed to sum over it. If you haven't seen that before, yeah, okay, let's not worry about it. Okay, so I've written it in a form that doesn't make it look like it's any easier. But let's go on to an orthonormal change of coordinates. Okay, and we're going to have, of course, the orthonormal change of coordinates we're going to go to eventually is the one where we change to the eigencoordinates. So I'm going to have coordinate x. I'm going to change to coordinate y, right? And this is going to be with orthonormal column vectors. Such a thing is called a unitary matrix if you've had enough linear algebra to see that. And of course, if the columns are orthonormal, then it's easy to find the inverse, it's just the transpose. Okay, so now I want to bring these two things together, right? I want to change coordinates and change my x derivatives into y derivatives. So I have to figure out how to do that. Well, I've got the du dxi. That's one of the things I've got in my PDE. If I want to change it to y derivatives, then I have a sum. I got to take the two y derivatives and multiply them by the chain rule thing, right? And this thing here, right, this is the matrix entry PKI. Okay, and if I take the second derivative with respect to xi and xj, right, then I have to take all of these things, right, and I have to do the chain rule on them, right? So I'll have 4 terms. I'll have d2u dyk dyl, and I'll have pki plk. Okay, so now I've changed this equation to y coordinates, right? And I've got, why are we performing this operation again, right? Because I'm going to show you that anything you start with will look either like the heat equation, the wave equation, or Laplace equation. Is that clear? No one's saying it's not clear. So I'll go on. Go back down. Should that be PLI at the end? No, it shouldn't be. I've got to convert the xi and the xj derivatives to y derivatives, and this is what comes out. I've already got the I ones here, right? Oh, now I see what you're saying, Juan. That should not be PLI. Yeah, it should be PLJ. So there is an error. It's just a different error than you suggested. Are we good? LJ. Okay, thank you. You'll notice in the notes that are posted, I've got it right in the next line, luckily. For the change of variables, where are the orthonormal column vectors coming from? Oh, this is just a general orthonormal change of coordinates. Any one you want. Of course, the one I'm going to pick later on is the one where I use the eigen vectors of the symmetric matrix A. Okay, so now equation 1 reads, okay, I'm going to sum over I. I'm going to sum over J. I'm going to sum over K. And I'm going to sum over L. Right, I've got the Aij. I got the PKI. Here I got this, right, LJ. And I've got all of these partial derivatives in the new coordinates. I'm going to have the sum of I equals 1 to 2. The sum of K equals 1 to 2. PKI, LI, DU, DYK. And all of this is equal to F of X. Okay, so now, again, this is chain rule meets linear algebra. There are, when you've done these things enough time, you know what comes out. So let me just say, I've got all of this summation notation, but I've got an interpretation of some of it in terms of matrix multiplication. So if I've got a matrix A times a matrix B, these are going to be 2 by 2. Then if I look at matrix multiplication, and I don't know if you guys still do this, but I've been at this a while and I still do this. When I think of matrix multiplication, I take the row of A, I turn it sideways, I take the dot product with the columns of B, right, to get the entries of the matrix C, the product. Okay, and if you think about that in terms of this summation notation, then to get the ith row, kth column of the product, you take the inner product of the ith row of A with the kth column of B, and so that's a sum of Aij, Bjk. So if I look at this sum, of Aij, Pki, Plj, right? This is equal to, this is just a complex matrix multiplication, right? It's a matrix, 2 by 2 matrix that comes out with entries K and L. Because I've summed over I, I've summed over J, so there's no I's left, no J's left, but I've got a K and an L. And if you use this idea, you can see that that matrix is the same matrix as the matrix P times A, right? I got the P times A from this one, right? But then you have a matrix with entries Kj, right? Multiplying something that looks like Lj, that's actually P transpose that you're multiplying by, right? It's got the entries swapped up. This is still our orthonormal matrix, so this is P A P inverse. Okay. So now this is where we're going to use the fact that A is symmetric. So we're going to take the matrix P to be, and the matrix P is telling us the coordinate transformation we're using in the PDE, right? So we're going to look at a new set of orthogonal coordinates, and they're going to be the ones that come from the eigen vector directions of the matrix A. So let's take P to be the eigenvectors normalized of the matrix A. And so then this whole thing and that matrix, right, that gives me a P inverse. This is the usual diagonalization process. It just gives me the eigenvalues lambda 1 and lambda 2. So lambdas, the eigenvalues of A. So that means this whole thing here collapses down to lambda 1 d2 u dy1 squared plus lambda 2 d2 u dy2 squared, right? And then there's some new coefficients. Right? Where these coefficients are just from the change of coordinates. Those are the easy ones. Okay, so let's have a look at this. That is f of p times the vector x. So that would be p of y, right? I guess if we're writing it in terms of y, it might be better to write this as, if that's the original function f, then this should be p inverse of y. Let me just make sure I've got my p's going the right way. Yeah, y is p of x. So the x would be p inverse of y. Okay, that's a good correction to make. So this already looks a lot simpler, right? Okay, we've gotten rid of the mixed partial derivative terms. We got something pretty simple. And here's where you can see 3 cases come out. So there's 3 cases. You can have lambda 1 and lambda 2 have the same sign. And then the equation is called elliptic. Okay, and then you can scale y1 and y2 further. Now I'm not changing the direction of the coordinates, I'm just scaling them so that you can end up with a u y1 plus u y2 plus a u x AUY1 plus BUY2 is equal to this F of, okay, transform coordinates. What do P, so these are just entries of the matrix. So this is the first component of the two, this is the first component of the, well, so these guys here, that's a row of this matrix P. So this is the first components of the two eigenvector, normalized eigenvector directions. Okay, so if you forget the lower order terms, then this is just the Laplace equation, or Poisson equation with the F. So no matter what you started with, right, there's a whole, right, here we started with something that looked kind of general. There's a whole class of those problems which under changes of variables just look like the Poisson problem, which is why we study it, right? Because it's not just representing this problem, it's representing a whole class that can come from a generalized setting. Okay, well, obviously lambda 1 and lambda 2 don't always have to have the same sign. They could have opposite signs. Right? And then after scaling, again, and taking the lower order terms equal to 0, right? We get and this is the wave equation. Right, so you would want to think of one of those directions as being a time-like direction in this case, and you would give initial conditions, right? In this case, and we'll see that possibly later today, depending on how the timing of the lecture goes. You can't give a Cauchy problem for the Poisson equation. It's really a boundary value problem. You have to give boundary conditions around, right, the outside of the domain you're interested in. And so just by that change of sign, you change the character of the problem quite a bit. What are the other things? Oh, there's a question coming in. Why do I write F dot? Well, because this now is an argument where I would have to write out not only the change of coordinates to get back to the original X, the rotated change of coordinates, I'd have to put in the scaling I use, right, to get these things, and that's just too complicated, right? It's something you can work out how to get back to the original thing. There's some forcing is all I'm saying over here. Is that clear?
So why was what we got after some transformation from the X kind of vector using like using the orthonormal matrix, right? And then you say, okay, and then you said, yeah, okay, we scale it for this. So I can think of it as like a function of a scaled version of y.
Yes.
Okay.
Yeah. So there would be the change, anyway, it's a change of coordinates you could use to get back from these new y's to x if you put your mind to it. Okay, so there's another one, right? So now the wave equation is not just describing itself, right? It's representing a whole class of problems. And in fact, there's only one other case. So I'm going to say if lambda 2 is equal to 0, right? Because here, right, if they have the same side or opposite signs, I'm implicitly saying they're not 0. So what if one of them is 0? Well, okay, you could say, what if they were both 0? So I'm going to exclude lambda 1 equals 0, because if both eigenvalues are 0, then this matrix A right at the beginning is the 0, has to be the 0 matrix, which means there's none of these terms, and it's not actually a second order PDE, right? It's a first order PDE, and we've looked at those separately. So if it really is going to genuinely be second order, then you can't have both of these zeros. Okay, so I'll write something in here. Exclude that one, since then the PDE is not second order. Okay, so if you've got that, then I have to do something a little bit more. I'm going to, here is where I've got to, right? I now know that this term is gone, right? I'm going to assume now, though, that this term is not 0, okay? Now, I'm doing that because otherwise, there's no y2 derivatives in this problem at all, and it's just an ODE for y1, right? So again, it's not a PDE. So now I'm going to assume that coefficient in front of, this is the coefficient of du dy2 is not 0, since otherwise it is just an ODE in y1. Okay, so if I do that, right, and again, scaling y1 and y2, I'm going to get minus uxx plus uy plus aux is equal to g of, I'll put g of x and y, okay, right? Right, so I'm going to scale these guys to x, this one to y, right? And I end up with something that looks an awful lot like the heat equation. Right, and those are the only 3 cases, right? So if you ever wondered, gee, why are we looking at these generic PDEs with easy coefficients? It's because they really represent everything that can happen in these types of problems. Okay, so let's notice a little fact from linear algebra, right? If you want to look at the product of the eigenvalues, oh, there's a question coming up. Did we set A equals B equals 0 in the case 2 of the wave equation? Yes, so that we could see the wave equation coming out. You know from the next assignment, well, you will know from the next assignment that you can have the wave equation with lower order terms. That modifies the wave equation to a certain extent. but you still get mostly wave-like behavior. So if you want to think of it a different way, it's the highest order derivative terms that drive the behavior of the model. And so the only reason why we've really focused on this lower order term here, this UI term, is because there wasn't a higher order derivative term in that direction. Oh, there's another question coming through. Oh, did I not say? Okay, that one was elliptic. Two, this is hyperbolic. And this one here, the heat equation is parabolic. And if you're wondering where these names come from, you can have a quadratic form, x squared, ax squared plus bxy plus cy squared is equal to a constant, right? This either gives you the shape is either an ellipse, a parabola, or a hyperbola. And it's exactly the same condition that decides which one comes from this. Okay, so that's where these names come from. So lambda 1 times lambda 2. If you want to figure out like which one it is, it's pretty easy, right? The product of the eigenvectors is just equal to the determinant. So all you have to do is to compute AC minus B squared, and it'll tell you whether, if that's positive, right, then you know that the two eigenvectors have this, eigenvalues have the same sign. If it's negative, they have opposite sign. If it's 0, then you know that it's this parabolic type. So it's easy to determine. And the only thing you have to remember is this B, right? The way I've done it is half of the coefficient in front of this mixed term. So you have, that's the only thing you have to be a little bit careful of if you use this formula. Okay, so let me make another note. And that is, let's say you have a variable coefficient problem, right? So if you've got back to the original PDE, if you have these coefficients that, oh, that's not a vector. If these coefficients depend on x, then the determinant of A, if those coefficients are continuous, right, then the determinant of A as a function of x is also continuous. You don't get exactly the same nice thing that happens, but basically this will tell you locally the character of your PDE. And if the PDE type changes in X, I'll just say that's tricky. That's outside of Math400. Okay, we're looking at problems, you know, which have a definite character. Someone right at the beginning of term asked me about, well, which type is Navier-Stokes equations in this language. So let me talk about incompressible Navier-Stokes. Well, it's got a bunch of different terms, right? It's not a single element of this class. right? It is, if you have a viscosity term, right, then really it's a parabolic problem, except that the incompressibility constraint is elliptic. It's an elliptic problem you solve. It's a global constraint. And then if you talk about the viscosity being small, right, which, you know, that's a high Reynolds number flow, then the terms that you're left with are wave-like convective terms, and so they have a hyperbolic character, and so it's not uniformly one of those three things. But then, you know, the Navier-Stokes equations you can't write in this simple scalar form, right? They're a vector equation with the pressure appearing in a different way, and the incompressibility constraint is a separate story. So there's lots of models where this type of insight is only a piece of what's going on, but it's an important thing to know, right? And certainly if you are in the business of modeling some new phenomenon as a first step to, let's say, doing some computational design work, then you kind of want to know what type of problem you have, so you know what type of numerical method to use. And even before that, well, you want to make sure of things like the problem that you are writing down is well posed and has the character that you think. Should it have wave-like behavior? Should it have diffusion type behavior? These are the sort of things you should know. And here's an easy way to find out. So there's an example in the notes, okay? So you can see how it goes. So let's just remind ourselves of what these three problems are like. So we're going to have the elliptic problem, right? That's got the representative scaled problem of let's say the Poisson problem, right? So this is Laplacian u is equal to f of x with boundary conditions all the way around. The simplest are homogeneous boundary conditions, homogeneous Dirichlet boundary conditions. That makes a well-posed problem, okay? For hyperbolic, we've got the representative wave equation. Right, that's UTT is UXX. And this is the problem the framework we're gonna look at for this type of problem coming up with the Fourier transform is the no spatial boundary condition problem, right? So I'm gonna have T and X going this way, right? And here I'm gonna give a U and its time derivative. So it's not boundary values I'm giving, right? There's no boundary value like in future time. I'm just telling you how things start out, right? The character here is F affects U at all points. The character here is, right, I've got this domain of dependence. Here, you haven't seen it yet, but U has two derivatives more than f. Right here, remember, if I start with a discontinuity, I just have a discontinuity moving with wave-like behavior. So here I can say U is as smooth as U0. So has the same number of derivatives. And then finally, we have the parabolic. And the representative here is the heat equation. And again, we're going to have the UT is UXX. You do have to give boundary conditions in X if there are boundaries. Let's just think about this infinite space problem, the Cauchy problem. Here I have to give a single initial condition. And we'll see that here U has an infinite number of derivatives. Even if U0 is discontinuous. Remember, yeah, the heat equation smooths things out, right? You can start with the discontinuity, but then that's built up of a bunch of high frequency information, and all of that decays really quickly. You don't see it anymore, right? So three types of equations, each of which needs different types of boundary data, boundary or initial data, each of which has a different character in the solutions. And let's go on now to look at Fourier series analysis of these problems in infinite space. What's the formal definition of a Cauchy problem? It's a initial value problem given in infinite space. We're going to see some coming up. Okay, so but now it's a review, maybe, of a Fourier series. Okay, so I'm going to consider a function f of x. And this is x in all real numbers, so all space. And you can get into all kinds of functional analysis of the Fourier transform. I'm going to do the easiest one. Okay, let's suppose that f is continuous. That can be relaxed to measurable, if you know what that means, and that the integral of its absolute value is finite. So f is in L1, if you know what that is. I'm assuming that most of you don't, but if you do, then this is stuff you've probably all seen before. Then I can define the Fourier transform. Okay, so Fourier transform is another function. I like using alpha for a wave number, but you could use omega if you really want to think of x as time and you want to think of its transform as a as a wave number, or as a frequency, angular frequency. So this is the Fourier transform. It's also defined for alpha, for every alpha, right? And it's defined as follows. You take f of x, you multiply by this thing, which has absolute value 1, and you integrate it, right? And because this thing was finite, this will also be some finite number that comes out, and that number is this value, okay? And we can write f hat is, it's an operator. You take on f. So it's a linear operator, the Fourier operator. So this is just notation. Okay, and if you want to recover the function back, it's an invertible operator. You just take the integral of the transform times these oscillatory components with wave number alpha. And this works pointwise with the conditions that I've given at the beginning. So this is f inverse of f hat. So why is this interesting? Well, for PDEs, you'll see why it's interesting coming up. The transform diagonalizes spatial derivatives. Just like the sine series was a diagonalized the second derivatives in all of the problems we looked at with zero boundary conditions, homogeneous Dirichlet boundary conditions. So this is the equivalent thing in infinite space. And if you looked for a function whose second derivative was a multiple of the function in infinite space, you would find this function, right? Except you couldn't really call it an eigenfunction because those functions don't have a finite weight. So this is something where instead of now a finite sum of eigenfunctions, you get this kind of whole spectrum of sort of eigenfunctions that you have to deal with. This is called the continuous spectrum if you go on and do more complicated PDE type work in infinite or semi-infinite domains. Okay, but that's what's motivating this thing, but this is just a concrete, well-studied, well-known thing. And from here, it's just a decomposition of your original function x into frequency or wave number representation. Okay, and there's a natural extension to square integrable functions. So if you've got the integral from minus infinity to infinity of the square of the function, if this thing is finite, you can extend the definition of the Fourier transform to these kind of functions. And then there's a kind of a nice thing that there's a relationship of the size of the function square integral between one and the other. By the way, I don't want to write anything down, but if you have seen the Fourier transform before in another context, it may have looked different, okay, right? Depending on which application it's, oh yeah, there's a comment, this is a D alpha. Yeah, thank you. Depending on which application you live in, these things get written differently. Okay, so it might be omega instead of alpha. Oh, here's another D alpha. Thank you. You may have seen omega instead of alpha. You may have seen this as plus, this up here as plus, and this down here as minus. You may have seen this factor of 2 pi over here instead of there. Or what I think is the nicest one, but involves more writing, so I don't do it, is that you see a factor of 1 over the square root of 2 pi in both places, okay? That's the sort of normalized version of it all. And in that format, then these things don't have the factor of 2 pi in them. But okay, it's equivalent. You know, your f hat might be the conjugate of my f hat, or it might be a multiple of it that's taken into account when you do the inverse transform. But either, you know, this is fine, right? There's some constants you have to worry about. Okay, so let's look at some of the properties of this thing. Here's the most important one for us in a differential equation course, okay? So if I take the Fourier transform of the derivative of f, well, let's just pretend we could take the derivative here and the derivative also behaved well enough that I could take the derivative inside the integral. I would just get a factor of I alpha. So if I look at this thing, this is just I alpha times f hat. So this says the transform, Fourier transform, diagonalizes derivatives. Right? Oh, fantastic, right? Now, every time we have a constant coefficient problem with the derivative in it, if we took the Fourier transform, we would just get this multiplication. Now, there's a bunch of convolution results. These are the things that are going to show up in what we're doing in a couple of places, but come up more often in signal processing, if you guys have seen that in any kind of signal processing course that you might have taken in statistics or in engineering. Okay, so here's what a convolution is. This is convolution. This is defined to be, now I'm going to take the integral from minus infinity to infinity. It's f of x minus s times g of s ds. Okay, and you can just write this out and you can convince yourself, if you take the convolution and then take the Fourier transform, that's the same thing as taking the Fourier transform product. And the way I've defined it, there's a factor of 2 pi that has to come here, okay? And if I take the Fourier transform of f times g, I get 2 pi times the convolution Okay, I should be more careful here. And I can read this backwards. And say that if I take the Fourier, inverse Fourier transform of f hat times g hat, I'll get 1 over 2 pi times the convolution of f and g. Okay, some other things. If I take the Fourier transform of a shifted version of my function, so I'm going to shift it to the right by a distance c, then I just get a multiple of the transform. If you've looked at the Fourier transform, then you've seen this, that Gaussians transform into Gaussians. So if I've got f of x is a Gaussian minus x squared over 2a squared, then f hat of alpha is a over the square root of 2 pi times e to the minus a squared alpha squared over 2. Okay, these are things that you can verify for yourself. Maybe I should have had a poll of who's seen all of this before, but from past experience, not everyone has seen these things. Maybe it's good to do. Okay, so the interesting thing here, which we'll look at, is that the Fourier series diagonalizes every constant coefficient linear Cauchy problem. Okay, well, let's see how that works. Well, let's look at ut plus ux is equal to 0 for x for the whole real line. And the Cauchy problem is I have to give initial conditions. This is our old friend, right? This is the one-way wave equation. We know that this solution should be just the initial conditions moving to the right. Okay, let's see how that goes, right? So at each x, at each time, let's take the transform. So I'm going to have u is going to be equal to, now I have to be a little bit careful. Where's my factor of 2 pi? Oh, here it is. no factor of 2 pi. I'm going to have u hat of t and alpha. Well, maybe I better go alpha and t, because I had x of t before. This is u of x and t. E to the, which sign did I have? This is the I alpha x1, d alpha. Okay, now I'm going to put that into the PDE, right? And I'm going to see that when I take the x derivative, right, all I get is a multiple I alpha times this thing, right? So I'm going to have two Fourier series, this and this, and I get to equate the coefficients of the Fourier series, and I get d u hat alpha dt, that comes from this. And then I get plus I alpha u hat is equal to 0. And I know that u hat of alpha is just u, the transform at time 0. Has to, these have to match up. And now you'll notice there's no PDE left, right? This is an ODE for each alpha. Now, if you think back to sort of sine series arguments, we had coefficients of sine series that obeyed ODEs. That was one of the first things we did for the heat equation. And it was a victory, right? Because instead of a PDE, we just had a family of ODEs. It was like a discrete countable family of ODEs, an infinite number, but countable. Well, so this might seem a little bit worse. Now we don't even, we don't have a sum anymore, right? We've got an integral. So we've got an uncountable number of ODEs to look at. But they're all pretty simple, right? I get the u hat of alpha into t is e to the minus I alpha t times the initial conditions. It's just a constant coefficient exponential solution, right? So that's what you get. And then I'm going to look at my transform properties backwards. And I'm going to see that for this behavior, then I have to have that this is just a translated version of the initial conditions. Right. Okay, well, we knew that was coming, right? Because we'd looked at this before, but that's kind of interesting. Let's look at the heat equation now in this infinite space setting. And, you know, funnily enough, I'll go to ut is u xxx next, which is like some new friend we haven't gotten acquainted with yet. This one, we also know what should happen. We're going to have exponential decay of large alpha components, and we'll get that. Right, and so I'm going to have initial conditions here. This is the Cauchy problem. Cauchy problem is you are taking one of the variables as a time variable, and you're giving initial conditions in infinite space for the problem. Okay, I'm going to do the same thing as above. I'm going to take the transform. When I take the transform of the second derivative, well, I take one derivative, I get a factor of I alpha. If I take another derivative, I get a factor of I squared times alpha squared. I squared is -1. So I'm going to get d u hat dt is minus alpha squared u hat. And you notice now I'm just putting a ordinary derivative, not a partial derivative, because I know that the Fourier transform is going to turn this into a family of ODEs. So for each alpha, there's no other variable in here, right? I've got these guys. And I'm going to get the same kind of story. I'm going to have, this is just exponential dependence, negative exponential dependence. So it's going to be e to the minus alpha squared t. U naught of alpha. So this is fast decay of oscillatory components. Just like we saw with the sine series in the finite domain. Well, and all the other series that we did. Okay, so let's just think about this though. That's a Gaussian. Okay, and this is a product, right? So if I put those two things together, I know that I can write U as a convolution with the Gaussian. Wow, okay. So this is the fastest way I know to get the Green's function for the heat equation, is just using these properties of the Fourier transform. So I'm going to say there's some algebra you can do, some of which is in the notes. But at least in principle now, you know that this has to be a convolution of U0 with a Gaussian, and it turns out to be minus s squared over 4t ds. And then there's a complicated coefficient in the front. Right? In this thing, t is just a parameter, and this is how that parameter comes into the change of Gaussian. Okay, now this is something which now you know what I'm going to say, right? This is a Green's function representation of the solution. Right? Why? Because it's an explicit map of how the data, and we've only got initial data in this problem, right? It's just Cauchy data. There's no right-hand side forcing term. So the only one we're talking about is how does the initial data affect the solution at later time? Well, this is it. This is the explicit map of the initial data to the solution. Okay, so let's make some notes though. This is where we get the global dependence, which we've seen before in different contexts. So let me just say that U of x and t for t past the initial point depends on all the initial data, right? Because this Gaussian is positive, right? For every, if you're at x for t bigger than 0, right? You've got, this is non-zero for every contribution from the data. Right, so there's this global dependence coming in. Remember, that's quite different from the wave equation, right? Where you have this finite domain of dependence. What are some other interesting things? Well, if I look at this Green's function, this is the thing I'm doing the weighted average of. This is this thing I'm doing the weighted average of the initial conditions of, right? Initial conditions closer to x, that's where s is small, right? Or have a higher weight. If I look at this, you can just show, right, that this is equal to 1 for all t. So when I talk about a weighted average, the total weight is 1. Right? Right? When I'm near x equals s, the weight is the biggest, right? Because that's where s is equal to 0, is where this has a maximum. And if I draw this thing, right, let's look at g of s and t. That's this thing that I'm convolving with, this e to the minus s squared, e to the minus s squared over 4t, with the normalizing coefficient divided by 4 pi t. If I look at that for t small, right, then I'm dividing by something big, right? But my Gaussian is very narrow, right? And if you're comfortable with the idea of a delta function, then formally, as t goes to 0, you get a delta function, which is exactly what you would expect, right? Because when you're at t equals 0, you should be seeing the initial data at that location, right? And if I look at t large, then my maximum value, if t is large, my maximum value is small, but my integral is still 1, and so I'm spread out very far. So as t goes to infinity, u of x and t sees an average of u0 of s values for s near x, and the interval where you're averaging over gets larger. I mean, it's never an interval, right? Because this function is non-zero, right, at every value of s. But, you know, it's exponentially small once you get far away, and that width of that exponential decay gets bigger and bigger. So you're averaging over more and more space. Well, there's a whole bunch of things we can do in this framework. And no one has told me that I've gone past 10:45. Gosh, I get so excited here. You're all so polite. Okay, well, we have a bunch more things we could do, right? Someone had said, what about UTT is UX? We can work that one out. We've got uxx plus uyy is equal to 0, Laplace problem. We can look at the Cauchy problem for that and see it's ill-posed. We can look at ut as uxxx. We can look at the telegrapher's equation, which is something you'll know about from your assignment, but we'll do all of that next time. Okay, and my apologies for going over not only the time I usually try and stop at 10:45, but my actual stopping time. So I'll end here.